Welcome to the Titus Timeout podcast. My name is David Sanders, and today we are going to be going over the source path receiver process for terminal units. The expectation for any modern HVAC system is that it should be felt but not heard. This holds true for not only HVAC equipment, but also air distribution components like terminal units. This is why great care must be taken on the front-end design process to mitigate any noise pollution that any occupant might experience that could impede function or comfort. To do this, an accurate acoustical model must be generated. AHRI Standard 885 specifies the source path receiver process to model the end noise that any occupant might hear. Let's look at how this can be done. In previous podcasts, it was discussed that there are two primary sources of sound that are generated by a terminal unit. Radiated sound is transmitted through the terminal unit casing or induction port of a terminal unit, which is omnidirectional around the unit. Discharge sound is transmitted through the ductwork from the discharge port of the terminal unit and propagates along the path of the ductwork. A third sound source comes from the sound that is generated by the outlet, which is typically in the occupied space. For acoustic modeling of the sound sources, a circle with the letter identifies these as sound sources and the type of source. The second part of the source path receiver process is attenuation. In any given path from the source of a sound to the occupant's perception, a number of different mechanisms can dampen the effect that the person hears. Some of the major sources of attenuation are duct breakout transmission loss, which is the attenuation ductwork provides from its radiated sound levels; flow division noise reduction, which is the attenuation of sound when the airstream divides; duct insertion loss, which is the reduction of sound between the entering and leaving section of duct; manufacturer's attenuation element, which is a noise reduction due to a separate attenuator used by the manufacturer, such as in the slide-out attenuator on our TFS-F Phantom unit; the ceiling effect, which is the noise reduction created by having a ceiling in between your plenum space and occupied space; duct and reflection loss, which is the attenuation of reflected low-frequency energy back into the ductwork due to a sudden area change; the space effect, which is the dampening of sound from a source in open space to the perception point within an occupied space; and elbow and T attenuation, which is the attenuation based on the change in directional flow of ductwork in elbows and T's. Now that we have our sources of sound and attenuation defined, we must plot the path of sound to the perceiver of sound. This is the basis of the source path receiver process. Let's do a simple example in acoustical modeling. Let's say that we have a fan-powered terminal unit in a plenum above a ceiling grid with a rectangular discharge which has a T and two flex connections to two diffusers with only one serving the occupied space of this model. This is all over occupied space, with occupants directly underneath the terminal unit. In this example, there are 6 separate paths of sound to perceive by the perceiver's ear. The first path is the radiated sound from the unit, which is attenuated by the ceiling. The second is the duct breakout from the initial discharge. This is the discharge sound attenuated by the duct breakout, then again by the ceiling. The third is the breakout after the T. This is the discharge attenuated by the first duct insertion loss, the T loss, the flow division loss, the second insertion loss after the T, the breakout from the duct, and the ceiling. The fourth is a breakout on the branch connection. This is the same path as 3, but with an added insertion loss at the connection and breakout and different breakout attenuation properties due to it being flex duct. The fifth is the full discharge path to include duct and reflection loss and the space attenuation between the discharge location and the perceiver. The final is the outlet generated path that begins at the outlet and is attenuated by the space between the outlet and the perceiver. Once these paths are mapped, a table can be created to map out all the different variables within each path. In another podcast, we will take a look how each of these variables and paths are broken down numerically to get a full acoustical model for this particular application. This concludes our podcast on the source path receiver process. Don't forget to subscribe to our YouTube channel, and thanks for taking a time out with us.